pleasure to have Lev Tovstopyat-Nelip, something like that, from UGA here to speak at our IMSA Topology seminar. He's going to tell us about quasi-positive surfaces and decomposable Lagrangians.
Thank you for the introduction and the invitation. It's nice to be here. It's a very nice campus. All right, so just to set some conventions, all three manifolds are going to be closed and oriented. All links will be oriented. So definition, a contact structure. Then on the side, on a three manifold Y is a maximally non-integrable two-plane field. Our contact structures are going to be co-oriented, so you think of them as kernels of one forms, kernel of alpha, where alpha, which d alpha, is a positive volume form. Okay, so the standard contact structure on R3 is just dz minus y dx, so the kernel of this guy, and a link L is Legrandrian. Well, in general. I'll say in general, then I'll draw the front projection picture. If alpha restricted to L vanishes. So if L lies in the contact planes. Okay, so if we have a Legrandrian in R3 with a standard contact structure, we can consider the projection to the XZ plane. And we get this front projection type picture. And there are no vertical tangencies.
What I did?
These are cusps over here. And I don't have to specify the crossings because the crossings always look like this. Okay? All right. Great. Let's talk about decomposable Lagrangians. Okay, so a decomposable Lagrangian in the symplectization of S3, standard contact structure, is a cobordism built up from elementary cobordisms associated to some moves. So the first move is called a birth. So locally, the front projection's empty, and then TB minus one unknot appears. Second type of move is a pinch. Okay, if you have a front projection that locally looks like this, you replace it with this guy. That's a pinch. There's another pinch where you flip all the orientations of the Legrandrians. And then the third move is isotopies. So Legrandrian isotopies. Okay. So that's a decomposable Lagrangian. And These were first studied by Sean Train. He proved that there are some constraints. So if S is a, well, he considered exact Lagrangians, which is more general, possibly, we don't know. From L1 to L2, this is all in the giant 3 spheres still. Then the rotation numbers at the ends agree, and the Thurston-Benneken number shifts by the negative one-order characteristic of the surface. Okay, so this is very different from the smooth category. In the smooth category, there are always linked cobordisms, and the question is, what is the minimal genus of a linked cobordism? Okay, here the genus is constrained, okay, by classical invariants of the Lagrangian ends.
So can you say what the word exact means? Because that's different than saying decomposable, or a priori it's different.
Yeah, I mean, a priori it is different. So exact literally means like an exact Lagrangian with Lagrangian ends. Decomposable is just sort of a way people came up with actually constructing these exact Lagrangians, and it's still open if every exact Lagrangian is decomposable. People don't know. Yeah. I don't really want to write too much.
Sure.
Yeah, it's not gonna actually talk. Okay.
I mean, I guess just for some others. I mean, one feature is that these don't go the other direction.
Yes, this is like having a exact Lagrangian from L1 to L2 is not a reversible condition. You could see that from the second equation. It's a direct relation. Okay. Yeah. So the main question here, we're trying to get at, is given L1 and L2, is there generally exact, but for us we'll just consider, is there a decomposable Lagrangian from L1 to L2? Okay. And in this talk, I'm actually going to consider decomposable Lagrangians in Stein cobordisms. So those are just, if you're familiar with Stein cobordisms, those are just going to be locally built up by these 3 moves plus Stein handle attachments on the complement of the Lagrangian in any slice. Okay.
For L1 and L2, are we not?
No. They can do links. So here's the first theorem. Okay, so suppose W is a Stein cobordism, from Y1 to Y2, and S inside the Stein cobordism is a decomposable Lagrangian from L1 to L2. So those are Lagrangian links in Y1 and Y2. Then there is a map from the knot-4 homology of the mirror of L2 to the knot-4 homology of the mirror of L1 that sends a certain Legendrian invariant in knot formology of L2 to the Legendrian invariant of L1. So, yeah, I'll explain what this is a little bit. Usually this T hat denotes the Braids transverse invariant, but here I'm thinking of it as a Legendrian invariant. So, if you have a Legendrian link, you can take the positive transverse push-off divided by L plus, and if you take the negative stabilization of the Legendrian, which just means you replace a little piece in the front projection that looks like this with a piece that looks like this, it doesn't change the transverse push-off. Okay. So it turns out all of the Legendrian invariants in knot formology are preserved by this negative Legendrian stabilization, so really they give rise to transverse invariants. Okay. So you should think of them as transverse invariants. Although just as an aside, if you want an actual Legendrian invariant, you could consider the pair of invariants where you're looking at the Legendrian invariant of L and the Legendrian invariant of L with its opposite orientation. Okay. Yeah, so here, if L is transverse, if L is Legendrian, excuse me, I just mean the transverse invariant of L is the invariant of the transverse push-off. Okay. So it's an immediate corollary. Suppose, well, so we have a Legendrian if the invariant of L is 0, or the invariant of L with its opposite orientation is 0, then L does not bound a decomposable filling in any Stein filling of Y. Yeah, I should say that this theorem was already proven in the case where you're considering just the symplectization of the type 3 sphere. So that was done by Baldwin, Widman, and Wong, but they used the combinatorial grid invariants. Okay? And their proof is like really specific to the setting they're working in. You can't really generalize it. The proof I'm going to give is very different.
When you say it is not bounded decomposable filling, you mean just is the boundary of a, so you've been talking about cobordisms, but then you want to say just go ahead and fill it off to like a closed format filters boundaries.
Yeah, if you want, I could phrase this as there's no decomposable cobordism from the TB -1 unknot at S3 to L.
To L.
Yeah, that's the same.
That would be the direction.
Okay.
Oh, because you'd be going to the empties, because you allow births, is what you're saying. It's the you could say it's it's just a cobordism from the empty link to
Yeah, it's the same. Okay, yeah, so I need to talk about open book decompositions a little bit. So let here S is going to be a compact oriented surface with non-empty boundary. Okay. And let's take diffeomorphism of the surface, which fixes the boundary point-wise. And then we're going to build a three-manifold from this thing. So first we look at the mapping torus. Which is this guy. So this guy has boundary consisting of a torus for every boundary component of the surface. Okay. And we're going to glue the solid tori so that P cross I mod this equivalence relation bounds a disk for every point P in the boundary. Okay. And we're going to get some three-manifold, some closed three-manifold. I'll call it Y sub the monodromy. Okay. Right. So it turns out that if you have, a surface and a monodromy, there's an associated contact structure. This is something classical now, proven by Thurston and Wincombe-Kemper in the 70s. But amazingly, if you have a contact structure, it always comes from an open book, one of these guys. So here, we say that S comma phi is an open book decomposition. For the closed three-manifold. Okay. So there's this Giroux correspondence. Which tells you that you can study contact structures on a closed oriented three-manifold via the open book decompositions of the manifold. Modulism, equivalence, you have to allow positive stabilizations and destabilizations. Okay, so going from right to left, this is Thurston, Wincombe-Kemper. And I need to explain a little bit about how to go from a contact structure to an open book decomposition. Okay. So here's a definition. This is something Giroux introduced. A contact cell decomposition of a contact manifold is a cell decomposition where, I'll call it X. The one skeleton is a Legendrian graph. Two cells are attached along TB minus 1 unnuts, and every 3-cell is a Darboux ball. Okay. So it's actually not too hard to see that every contact structure or every contact manifold admits a contact cell decomposition. But Giroux introduces this notion to show that, given a contact structure, you can come up with an open book giving rise to that contact structure. His idea is the following. So given such a contact cell decomposition, what you can do is you can consider the ribbon of the one skeleton. This is a surface that retracts onto the Legendrian graph that's determined by the contact planes along the Legendrian graph. It turns out this is a page of an open book. Supporting the contact structure. Okay. Okay.
The binding is X prime.
No, the binding is not X prime. So here's a picture. Say here's an abstract picture. Okay. Say here's your page. Okay. Then you know a little contact geometry, so I'll just tell you. Then this is a Legendrian graph, and the ribbon of that graph is just the surface determined by the contact framing, which agrees with the page frame. So the ribbon of this graph is the page. Okay.
So
Yeah.
I'm the understanding that this correspondence is not, there's some work to be done confirming it. Is that kind of somewhere contained in here? You said it was straightforward to see that there's
No, it's not quite contained in here. I think it's in proving that if you have two open book decompositions giving rise to the same contact structure, then they're actually related by stabilizations and destabilizations. I think that's where the ambiguity is. But this construction definitely holds. Okay. All right. Okay, so let's look at a super simple example.
Yeah, we can talk about that at lunch.
Okay. Let's look at S3 with the standard contact structure. Well, here's a contact cell decomposition. Here's the one skeleton, and then there are two cells. There's one here, and one that's the rest of the whiteboard. And then 2 3-volts. What's in front of the whiteboard and what's behind it. Okay. Okay. So the ribbon of this guy is a hop bin. So there, the open book you're looking at is just the annular one where you do a positive twist along the core circle. Okay. There's an even simpler decomposition. Right. Actually, does the trivial open book come from this construction?
I mean, you can think of a vertex, single vertex.
Yeah,
as
that's
a
what I was
Legendrian
thinking.
graph. Yeah. And then you just have a single Darboux ball. There's no two. You don't need any two cells.
Yeah. So another way to get an open book, another open book supporting the standard contact structure is just the one with disk page and trivial monodromy. So a little more intuition about open books and contact structures. So here we're looking at disk with identity monodromy. Let's think of the boundary of the disk as the z-axis here. So the contact planes, let's think of them as the kernel of dz plus r squared d theta. This is like the rotationally symmetric contact structure. It's the same as the standard one.
It's contactomorphic to the standard one.
Yeah. Okay. So along this binding, the boundary of the disk, the z-axis, this is what the contact points look like. In particular, the binding is transverse to the contact points. Okay, and if you get far enough away from the binding, the contact planes become arbitrarily close to the tangencies of the vibration of the component of the z-axis. Okay, so if you get really far away, the contact planes look almost, vertical or locally integrable, but they're really not. Okay, so why am I saying this? So Bennekin observed that if you have a link that's in the complement of the z-axis and positively transverse to the fibers of vibration of the component of the z-axis, then it's transverse to the contact planes. Okay. So in other words, closed braids about the unknot give rise to transverse links. Transverse meaning positively transverse to the contact points. Okay. So closed braids about the unknot, those are just conjugacy classes in some Artin braid group. Which we're going to think of as the mapping class group of the disk with a bunch of punctures. Okay. Okay. So amazingly, you can upgrade these ideas, or maybe not too amazingly. You can see that braids about an open book decomposition. Here I just mean a braid in the complement of the binding of the open book that's positively transverse to all the pages are naturally transverse in the supported contact manifold. Okay. And this was fully fleshed out by Pavlescu, this sort of relationship. It's called the transverse Markov theorem. So, transverse links in a given contact manifold up to isotopy corresponds to braids about, let me state it this way. Let's say the contact structure comes from this open book up to some equivalence, which is positive Markov stabilization. So in the standard braid group, positive Markov stabilization just looks like, here's beta, you add an extra strand, one positive crossing. It clearly doesn't change the isotopy class of the closure. In fact, it doesn't change the transverse isotopy class. Okay. Great. So the contact structure, the contact invariant in Ungar formology is defined using the Giroux correspondence. And Baldwin, Velovic, and Vertesi, they define this braid invariant using this theorem. In a completely analogous way. actually, yeah. Almost the same. You can think of it as the relative construction. Okay, so one property of this transverse invariant I need is co-multiplication. Okay. So for Braids, I proved this, but for the contact invariant, this is due to John Baldwin, and there's no real original idea here for Braids. It's just that I wrote it up. Okay, so given pointed mapping classes alpha and beta, okay, we can consider the composition beta with alpha. That's going to give a link in some manifold, a transverse link in some contact manifold, and we can consider the closures of alpha and beta individually. So there's actually a map associated to this, which goes from the knot form homology of the closure of the composition to the tensor products of the knot form homologies of the closures of the individual monodromes. Like this. Okay. And it sends the invariant of the closure of the composition to the tensor product of the invariants of the closures of the two parts. Okay. Yeah, so the proof of this is just some small triangle counting argument. Right. Not going to get into that. So using co-multiplication, I actually prove another theorem from which theorem 1 follows. So here's theorem 2. Okay. So suppose sigma sits inside the page of an open book decomposition in the interior. Okay. And the boundary of sigma is K1 union minus K2. So think of it as, minus means orientation inverse. So think of it as a cobordism from K1 to K2. Okay. Such that K1 lies in the same component, I'll draw a picture, of the page minus the interior of the surface as some part of the boundary of the page. Then there is a map associated to sigma sending the transverse invariant of K1 to the invariant of K2. So here's a picture.
So sigma is connected.
It doesn't. Yeah, let's say it's connected. It doesn't really have to be, but then you have to change this hypothesis a little bit. You'll need that every component of K1 lies in a component of this guy as some part of the boundary.
Yeah, I mean, I guess it's, just say like K1 was the boundary of one component, K2 is the boundary of the other component.
Uh-huh.
I don't know. I mean,
I see. You know, for now, let's just say sigma is connected for simplicity. That's the case that is relevant here. Okay. So here's the picture. Maybe this is the whole page, and then this guy here is sigma, and the bottom boundary component is K1, and the top boundary component, which here is disconnected, is K2. Okay, so it can be a link. All right, so there should be an immediate question like, why are K1 and K2 even transverse here? And why are they transverse? All right, well, there's a couple of different ways of thinking about it. On one hand, to get a transverse rep of K1, you could use something called Giroux flexibility. Another way that I like to think about it is to consider something called a push map. I should explain this. But you take a piece of K1 and you drag it to a collar neighborhood of the boundary where the monodromy is trivial, okay? Like this. And you take K and you braid it as an index 1 braid about the open book. Okay. So you can imagine, here's like the picture in R3. That's the z-axis, the binding of the disk open book. Here's K, and then what I've done is I've taken K and braided it as an index 1 braid. Okay. That's exactly what's going on. And so let me explain push maps and half twists. Okay. So given gamma connecting two marked points and in the surface, maybe here's P1, here's P2, here's gamma. The positive half twist about gamma is supported in the neighborhood of gamma. Let's say this neighborhood. And it's determined by where it sends this red arc alpha. Okay. And the image is this blue curve, beta. Just like this. This is the analog of, an Arden generator. Okay. And we also need a push map. So given a simple closed curve, oriented, simple closed curve going through one marked point, P. So let's call the simple closed curve maybe K here. Okay. The push map of P along K can be expressed as a composition of two Dane twists. So first, we do a positive Dane twist here and negative Dane twist here. So if I call this gamma and this one delta, it'll be tau gamma composed with tau delta inverse. And which one's positive and which one's negative is determined by the orientation. Okay. The way I like to think about it is this corresponds to the closure of a push map corresponds to an index 1 braid, and it's sort of a movie of how that braid intersects the pages as you flow through the monodrome. Okay. So that can be a little bit confusing. All right. So now I'm going to explain the proof of Theorem 2. Proof idea. Yeah. So it's sufficient to construct the map for both pairs of pants. Okay. The merge and split. Okay. I'm gonna just draw the picture for the split. Okay, so here's sigma, here's K1, and here's K2. Okay. So sigma is sitting inside a page of an open book. I'm going to isotope it within the page so that this bygone region is in a color neighborhood of the boundary of the page that's fixed by the monodromy. Okay. If we do that, then the closure of this one braid, I'll call this K1. If you take this push map and compose it with the monodromy of the open book, and you look at the closure, this is exactly transversely isotopic to K1. Okay. Now we're going to do one more thing. We're going to positively Markov stabilize once. This here is gamma. That corresponds to adding another strand, so one more marked point, and then looking instead at the closure of the composition of the push map with the half twist with the monodromy. Okay. Okay, so on one hand, the closure of this is K1. Okay. But now this monodromy is actually equivalent to another monodromy. This is still a bygone fixed by the open book monodromy. And here, we still have gamma. Okay. Maybe I'll call this curve K21 and K22. Then, if you look at this composition, so first this push map, then this half twist, then this push map. This is actually exactly the same as just doing the original push map and then the half twist. Okay? The way you prove that is like the usual way. You cut the pair of fans up into two discs, each containing one marked point via some arcs, and you see where both of these send those arcs, and automatically you get this. Okay. So in particular, if you compose with the open book monodromy, you get the same thing. Okay. So now, co-multiplication basically gives you a way of getting rid of this positive half twist. There's a map associated to getting rid of the positive half twist, and then what you're left with is just a braiding of K2. Okay, if you delete this positive half twist, you see that you have a braid corresponding to K2. Okay. So co-multiplication gives you the map, essentially. All right. And there's a similar picture for the other pair of pins.
Just because the associated convex-free manifold is like S3, and T invariant is 1.
Oh, and the piece you're deleting.
Yeah.
So
Is that what happens? I mean,
it's actually a connected sum of tight S1 cross S2s, because you have like a non-trivial page with trivial monodromy, but it is a TV minus 1 on not. Yeah. So that's the part you're questioning away. Yeah. I just didn't want to write that. Yeah. I mean, the real upshot of co-multiplication is the pointed monodromies giving rise to transverse links with non-trivial invariant form a monoid. Okay, and here you can always conjugate, so without changing the transverse closure, so you conjugate and you get rid of that positive back twist. Okay, I mean,
Sorry.
yeah.
The hypothesis of this, like this weird boundary component part, just for the push map to be
Exactly, yeah. It's to get this little flag on.
otherwise, okay.
Yeah.
You can't get rid of, like, it has to be there.
It has to be there, yeah.
Okay.
Yeah. Yeah, it has to be there.
I mean, just in order to get that equality.
Yeah.
To even like construct the braid whose closure is K1, you need to be able to like drag it towards the boundary.
Yeah.
Yeah, so that's the idea of theorem 2. Yeah, how does it apply to give you theorem 1? Okay, so to prove theorem 1, well, you have to consider a bunch of different moves. So birds, isotopies, and Stein handle attachments. Turns out these are all easy. But pinch moves are more interesting. So I'll just explain what to do for a pinch move. So there are two oriented pinch moves. I'll just draw the picture for this one. So this here is going to be L1, and this will be L2. Okay. So the first thing I'm going to do is I'm going to negatively stabilize the bottom part of L2. So it looks like this. Okay. And the transverse invariant of the transverse push-off is unchanged when you do this. Okay. And then I'm going to consider a graph, a Legrandrian graph gamma, which kind of looks like it contains L1 and this L2 negatively stabilized. It's like this. Okay. So here's gamma. And then I'm going to look at the ribbon of gamma. You can draw that in the front projection. There's two colors here. This is what it looks like. Let me shade it in. That's the ribbon. Okay, and the boundary of the ribbon, well, it's actually just this guy. So that's the push off of L1 union the push off of the stabilization of L2 with its opposite orientation. Oh no, usual orientation. Opposite orientation. Okay, and then here's the trick now. You can take gamma, and you can extend gamma to the one skeleton of a contact cell decomposition. Call it X1. So then the ribbon of gamma is contained in the ribbon of the one skeleton, which is a page of an open book supporting the ambient contact structure. Okay? And then theorem 1, theorem 2 gives the desired graph. So that's it. There are two key ideas. First, the map associated to a quasi-positive surface coming from co-multiplication, and then how do you apply that to figure out the map associated to a pinch move?
All right, well, thanks.